Okay, so the really last video I want to do here is going to be about Cayley's theorem and then just a little bit about group actions in general. So I'll do Cayley's theorem first, which is an example of a group action. There's a weak form and a strong form. I won't actually do the strong form. I'll show you in the notes where I do have the strong form. The strong form, I'll just say what it says. It basically says that to every group, we can find a structure whose automorphism group, which basically means the group of symmetries, right? So you move things around, but it looks exactly the same, right? Is exactly isomorphic to G, all right? So that's a theorem, which is interesting. So that's kind of the strong form of Cayley's theorem. The weak form of Cayley's theorem is just going to basically say that we can find a subgroup of the symmetry group on G, right? So G may even be infinite here. This is a case where we might use infinite symmetry groups, which is isomorphic to G. So it's weaker in the sense that we're not saying we have a structure whose symmetries are exactly equal to G, right? But that is actually also true. So that in some sense, being the symmetries of a structure is exactly what being a group is, right? So it's a nice kind of almost philosophical thing. The weak form is going to be this. So I can find what's called an action on G, right? So we'll have G going to G. Let's see. I guess I really want to say we have G. We have an operation G cross G is going to G. Okay. And the operation, I'm going to just call this, I will also call this dot, okay, because it's common to do that. And in fact, I guess in some sense it's often denoted with like a lower dot instead of a dot right in the middle to distinguish it from multiplication. And the operation will be G dot H is actually just going to be GH, right? So that's all it is. I want to make sure, let's see. So I guess I want to look at maybe I actually want to look at, think for a second. No. Yep, that's what I want. Okay, because there's left and right actions, so I want to be a little bit careful. So I'm gonna stick with what I said. So G dot H is going to just equal to GH. Okay, so here's a claim. So this you might also define as phi G. Right, so it's different than the inner automorphisms we had before. This is not going to be an automorphism. It won't preserve group structure and things like that, right? So the inner automorphisms were automorphisms. This is not an automorphism, but it is going to be, in this case, a permutation of G, right? So one claim will be this. So claim is that phi G is in SG, right? So a symmetry, not an automorphism, but a symmetry. So to show that, we need to show that that it's one-to-one and onto, right? So let's see. So let's do one-to-one. So if phi of G of H equals phi G of H prime, right? So this is just saying the same as G dot H equals G dot H prime, right? In this notation. And I'm sort of introducing both these notations because they're both just common. I mean, sometimes it's useful to think of it like this. This is often the notation for an action. Okay, so but what is this? This is just GH equals GH prime, right? Well, clearly I can multiply on both sides by G inverse, right, and get that H equals H prime. Right? So in other words, if this happens, then H equals H prime, right? So it's one-to-one. Let's see, it's onto, right? So let H be an element of H. We need, let's see if we can just figure this out. We need some H prime such that G dot H prime equals H, right? So what is this? Well, this is just GH prime should be H, and it's pretty clear that taking H prime equal to G inverse H will work, right? If I just take that. So then I get that G of G inverse H, right, is equal to H, right? So it is onto, right? So it's onto. So each phi of G is in SG. So phi of G is in SG, okay? Let's see that the set of phi G, such that G is G, right, is a subgroup of SG, right? So in other words, I want closure under, multiplication and all that sort of stuff, right? There is, in this case, closure under composition. And the real point here is that phi of GH of K, so this is just like what we had before, is actually phi of G phi of H of K, right? Why is this? Because this is just GHK is equal to GHK, right? So this is actually associativity, right? So writing this another way is GH, in fact, just to put the parentheses, GH dot K, right, is equal to G dot H dot K, right, like that. Okay, but writing this is, so this is saying, this thing moves K. So, and what is this? Well, this is really phi of G of phi of H of K, right? So what this is saying is that phi of GH, whoops, phi of GH gets mapped to phi of G compose phi of H, right? So like that. So this shows closure under composition, right? Because if I take two things which are in that set, well, they come from some G and H, and so I can take the product on this side, and that'll give me the composition on this side, right? Let's see. I also need that phi of E. I guess this I didn't prove in the inner automorphism part either. So phi of E, I want to say is the identity, right? So we want to say the identities in there, right? And that's pretty clear because phi of E of H, right, is equal to E dot H, and that's equal to EH, which is just H, okay? And so it sends H to H, so it's the identity, right? So we got that. And that's all I actually needed, right? So it's, oh, and then what else do I want to say? So it's definitely a subgroup. Let's show that this map, okay? Let's show that the map phi of G, G maps to phi of G is actually 1-to-1. Now this I couldn't do, right? Remember I tried to do this with inner automorphisms before and got myself confused, right? So that wasn't true with inner automorphisms, but it is true here. So let's say that I have, let's see, how do I want to show this? I want to show that, let's see, there's a couple of things I could do here, but I guess I just want to say if phi of G equals phi of G prime, right? Then I just need to show that G equals G prime. There's a couple of ways of attacking this, but let me just do it this way. Because this is what it would mean to be 1-to-1, right? And so what I have here is I have GH equals G prime H, right, for all H. Well, then I can multiply by H inverse for any H, right? But I could also just apply it to E, right? So I get GE is equal to G prime E, right? And so G equals G prime. So there's all sorts of ways you could do this. I'll mention one thing in just a second for this too. But what this tells us, right, is where it says this mapping, G getting mapped to the set of all phi G, G and G, right, which is actually a subgroup of SG. These are the symmetries. Well, the symmetries of G, the automorph. One-to-one onto mappings of G to itself. They're not automorphisms, right? So we're just saying all of the bijections of G with itself, right? But that is a group, right? This is a symmetric group over G, right? And so this is now a subgroup, and since it's 1-to-1, right? This group here is just basically the same as G, right? So it's isomorphic to G. because this just maps, unique thing to unique thing, right? And it's a subgroup of here. So G, so you can just think of, if you want, you can think of G as being a subgroup of SG. Right, so that's kind of the weak form of Cayley theorem. Good. Let's see. One thing I wanted to use a second ago, I'm just going to mention this, and it's a little bit of sequence here, is that if I have a map, homomorphism phi from G to H, all right. So I've had to a couple of times try to show something's one-to-one. And what I want to say is that phi is, and this is familiar from linear algebra, phi is one-to-one if and only if the kernel of phi is the identity, it's just the singleton identity, right? So remember, this is always a subgroup, so that's kind of the smallest subgroup it can possibly be, right? And so, so this is clear, right? So if phi of, let's say phi is one-to-one, we'll do both directions of this, right? Then I'm going to have that phi of H equals phi of H prime implies, right, that phi of H, the H prime inverse is E. I guess I have to do a little bit of work here. All right, and so this is phi H, and this is, remember that phi H prime inverse will actually be phi H prime inverse, right, like that. So we proved that before, right? I mean, that, because it preserves inverses. I mean, that wasn't part of the definition, but we proved that that's true, right? And so I can combine, well, okay, let me do one more. So phi H prime, let's see, put parentheses all over the place. Yeah, like that. Oh, sorry. I'm getting myself. So, let's see, not writing what I want to write here. So I want to put phi. So phi H prime inverse, quantity inverse is phi H prime inverse, right? So this is that's what I wanted to say, right? So now I use the fact that we have congenital products to be H prime inverse, right? Like that. And so if these are the same, this is equal to E, right? But this tells me that H prime inverse, right, is equal to E. And you can flip this around the other way and do H prime inverse H is equal to E. So in particular, uh, oh, sorry, I don't even have to do that, right? So I just multiply both sides, so I get H equals H prime. That's all I want, right? So I just multiply both sides by H prime inverse, right? And so start off with phi H equals phi H prime, get H equals H prime, right? So if phi is one-to-one, right? What am I trying to say? Let's see, I got myself totally confused here. Let's go. I'm just gonna leave this in. Maybe I'll go back and cut this out. Maybe I'll just leave it in. I'm trying to show if it's one-to-one, then the kernel's E, right? So I'm going to say if phi of, so I'm assuming it's one-to-one, suppose phi of H equals what? Equals the identity of phi of G, right? So that's something G equals the identity of H, right? So that's what I'm trying to say. Then I want to show that G has to equal the identity, right? So yeah, this was even easier. Sorry. So this clearly, so I'll just decorate these for just a second since I've got myself confused already, right? It's clearly the case that that's true. Since it's one-to-one, right, G has to equal EG, right? So that says, so this says the only way that I can map something to E is if it was starting out to be E. So this tells me that the kernel of phi is E. Singleton EG, right? Going the other way, right? So this is what I was trying to do a minute ago, right? So suppose phi of G equals E, and this is H, right, implies G equals EG, right? Sorry, EG. So that's saying that the kernel, the kernel of phi is e.g. So I'm assuming that, right? Then I get this. Now suppose phi of g equals phi of g prime, right? Then what I'm going to get is that phi, then I'm going to do the argument that I just erased a minute ago and get that phi of g prime inverse equals e, right? But that's going to tell me that g prime inverse equals e, right? And that in turn will tell me that multiply both sides by g prime, and I get that g equals g prime, right? So I get one-to-oneness, right? So if this happens, then that happens. Right? So that's where I was getting myself confused a second ago. Okay, so that was just sort of a little side note, right? That if you want to tell if a function is one-to-one, you can check the kernel is trivial. Now, this is something you also know from linear algebra. That's the reason I wanted to put it there. And also, it's something I tried to use up here. So I just wanted to get it out there.